Hi everyone, we're going to do an introduction to the section 3.5 reading, which is on derivatives of trig functions. So first of all, why? Why are we studying these things? Why do we care? Always a good question to ask. So there are a lot of things in the world that are interesting, that scientists are studying, that are periodic, which means that they repeat themselves over and over again. Things like respiration or heart rhythms or tides or sound waves or light waves or anything that you can think of that repeats itself over and over and over again. These are things we want to study. These are things that scientists are studying all the time, and we want mathematical models to be able to study those phenomena. And then there's a remarkable theorem, if you go on to advanced calculus someday, that says that any periodic function, something that repeats itself over and over again, can be written in terms of these sines and cosines. And so if we can understand these basic building blocks, the sines and cosines, then we can study basically anything that's periodic, right? Which is really, really, really powerful and amazing. And of course, one of the questions that we're always going to ask is, how is it changing, right? You're looking at that heart rhythm, right? Is it increasing? Is it decreasing? Is it increasing slowly? Is it increasing quickly, right? And so we want the rate of change, which of course is the derivative, which of course is the main object of our study for this entire semester. So why, right? We want to study periodic phenomenon. Periodic phenomenon. Again, anything, respiration, heart rhythms, tides, sound waves, anything that repeats itself. Okay, so what we'll do now is we'll just take a look at one of our most basic trig functions, the sine graph. So we look at sine of x, which we all know, right, and have memorized as part of our fundamental outcomes, the sine of x graph. It looks like this. And we know that the derivative is the rate of change, which is the slope of the tangent line, right? So derivative. So we want to find the derivative of sine of x. That's our question. Always know what your question is. And we know that the derivative, just generically speaking, is the rate of change at any particular point. And it also is the slope of the tangent line. And so as we've been practicing, right, we can look at the graph of a function like this sine of x function and just kind of estimate, guess what the different values of the slopes of the tangent lines are at different points. And then from that, plot an approximate graph for what we think the derivative of sine of x is. And right, sine of x, just to give a little bit of a preview, right? Sine of x is repeating itself. It just repeats over and over and over and over again. And so those tangent lines, right, to the curve, right, whatever it is here, it's going to be the same thing over here. It's going to be the same thing over here, right? Whatever that value is here, it's going to be the same. It's going to be the same here. So we expect the derivative of sine of x is another periodic function, right? Which means it can also be written in terms of sines and cosines. So just a little bit of something to keep in the back of your mind as we do this. Okay, so let's draw in some tangent lines. And when I draw in my tangent lines to try to draw the graph of the derivative of a function, what I like to do is I like to anchor them at the zeros. And so in particular, the sine of x graph, it has these nice hills and valleys, and it has slopes of tangent lines that are zero at exactly the tops and the bottoms, right? The tops of each hill, right? And the bottoms of each valley, those slopes of the tangent lines are zero. And so the derivative function, which I'll draw in a different color, how about green, is the derivative function actually, the value of the derivative is zero at exactly those points, at minus 3 pi over 2, at minus pi over 2, at pi over 2, the slope of the derivative is zero, at 3 pi over 2, the slope of the derivative is zero. Okay, so what else can we say? So you can prove, it's not easy, it'll be in the textbook, that the derivative, the slope at zero, is exactly equal to 1. So that value exactly equal to 1, which means this value over here also equal to 1. And as you can probably guess, these things are symmetric, right? So this value here is minus 1, and this value here, the slope is going to be minus 1. So we can also plug those values in and plot them on our graph, right? So over here, the value is 1. That means at 0, the value of our derivative is 1. At pi, the derivative is -1. We can plot it in. At minus pi, the derivative is -1. It's decreasing, right? It's going to be a negative number. At minus 2 pi, the derivative is +1 up here. Okay. And so we can already see if we're starting to connect these dots, right? It's going down, it's going up, it's going down, it's going up. And so you might already be able to guess, right? A periodic function, a trig function, where the value at 0 is 1, right? The value at pi/2 is 0, the value at pi is -1. And it will turn out that, in fact, the derivative of sine of x is exactly cosine of x. Right, we can try to draw it in all nicely and neatly. Over here at 2 pi, it's also going to be +1. I should have done that one. Come back around over here. Right, one of the things we should be noticing when we're doing our graphs for F4, right, they should be nice and curved like this, not pointy or straight lines like that. So it turns out, we haven't proven it, but this gives some kind of an idea that the derivative of sine of x is cosine of x. This is true, it's a fact. And then you can do the same process yourself to try to figure out, right, what's yours. Do the same exact process. What's the derivative of cosine of x? So I'll leave you with that and enjoy the reading.